Welcome, everybody. I'm glad you could make it to this great event, and it's great to be part of it, too. And I hope you're looking forward to a whole day slate of great talks. What we're going to be talking about now for the next few minutes is talking about new things, because we've all worked on new things or been users of new things. And this talk is about how to answer, why will this new thing somebody's trying to pitch to you, maybe to get their project funded if you're the manager who controls the budget, or if you're the user who wants to use their product, or if you're the one who's trying to design a new thing, why is yours going to succeed when a bunch of others that look just like it have failed? And so as we talk about that shining city, we're not going to talk about some basic stuff that everybody had better do right in execution. I'm not going to talk about agile versus waterfall. Not going to talk about making sure that you're properly funded, that you have a good design team, a good implementation team, good marketing. I'm going to assume you nail all those things, because generally when you wonder why did something succeed when others failed, those ones are obvious. You can point to those things. Those aren't design differentiators. What we're going to do instead is we're going to talk about strategic differentiators that are about how we design our product, usually right from its inception, in order to be able to unblock success. Doesn't guarantee success, but it unblocks and accelerates success. And we're going to focus on three specific things: value, the value proposition, the availability, where this design is designed to be used, and how both relate to the main topic, which is compatibility. So let's talk about those things, but let me define what new thing means. When I talk about a new thing, it can be either a brand really new thing, a competing new product. We're going to be talking about programming languages, so it can be a new programming language. Or it can be the next version of your current product, because once you're established, that's the same thing. When you're the incumbent, your next version's biggest competitor is the previous version that's out in the field. Or if you're unlucky, sometimes several versions ago, if you haven't been able to bring your customers forward. Just having the same name, even for a programming language, does not guarantee acceptance. This is why Visual Basic to this day, after taking a big breaking change, still has 2 Wikipedia pages, because they have the same name, but they're 2 different languages. So let's talk about the value proposition first. That shining city on the hill and how you explain it. So we're all familiar with the elevator pitch. You need to be able to corner your customer or your CEO in an elevator, and on a 30-second ride, explain, well, why should they care about your product? But how do you do that? Well, the easiest way is to focus on known pain points with some existing established old thing. And that accomplishes 2 things right away. First, it gives you a strong connection to something they already understand. And that also orients them by saying, you're starting here and we're going to take you in this direction. So instead of having to explain a whole new greenfield product, you reference, anchor on something that exists, and then you're only explaining a delta, and you're doing it in a compelling way, you hope, by addressing a known pain point and explaining how you're going to solve it. So when you look at JavaScript successors or complementary languages, there have been several, including Dart and TypeScript, and they've had a pretty easy time of making a value proposition like that. JavaScript is absolutely useful and critical to our civilization, and it has known pain points. So making the value proposition of JavaScript, but better in the following way, that addresses pain points, is a very easy way to make an elevator pitch. Other languages have this opportunity as well. So once you've established that value, let's broaden our horizon a little bit and say, who are we going to get there? How are we going to start bringing people to that value by making it available? This affects design. You have to design for an availability strategy. So here's what we're trying to achieve. You want to be available anywhere an old thing already is used, and make it easy to add to an old thing project. So if you've got a new language, you ideally want it to be available anywhere where the existing language that it's competing with or trying to improve on is already available. And you don't necessarily need to actually be in all those places in your first release. That helps. But you need to design upfront to plan to have no architectural blockers that will prevent you from achieving that. It has to be an explicit design goal right up front. Let's look at some examples. The C programming language grew up in a time when there was a proliferation of systems language, but there was one for each hardware platform. And as Bjarne Stroustrup says, speaking of Dennis Ritchie, they said it couldn't be done, but he did it. And well, what it is portable performance, to have a language that is the same language on multiple divergent platforms, but that compile to pretty efficient code that's in most cases competitive with a hand-tuned language, custom language for that hardware. And that was mostly true. There were some outliers, and just the existence of C drove some convergence into PDP-like systems, but it achieved something that people said couldn't be done. And it succeeded because it was designed to be available on a large range of architectures. The next three examples, C++, Python, and TypeScript, actually have a very similar story together. The very first C++ compiler, CFront, compiled all C++ programs, including itself, down to C, and it could be used anywhere where C is used. That includes that because it was competing with C to be a better C, it automatically used the C optimizer. Didn't have to go and build its own greenfield. It used a system linker. That's compatibility. We'll talk about that in the third section. And similarly, CPython, the reference compiler that's still in use today, was written in C. And so even if we developed IronPython and others eventually, well, just having CPython out of the gate gave you reach. It was available wherever C was available. TypeScript compiles to JavaScript. It's available on any JavaScript runtime. Swift and Roslyn have a slightly different story, but it's the same availability design. Swift and Roslyn were each made available to their company's IDE on every platform that IDE supported, Xcode and Visual Studio, and on every platform that Objective-C and Visual C# supported, and then broadened from there to support additional platforms. The originals didn't, but they were there where the customers already were using NewThing, and they were available. That wasn't an accident. That was by design. We'll have some more details in a few minutes. But now both of these relate to compatibility, which is this bridge at the bottom of the screen. How do we now get people to that glorious endpoint where they get the value that you've proposed to them? You've made it available, but now how do you onboard? How do you migrate? How do you get them to actually be able to adopt it? Well, anytime a user looks at a new product, they're going to put forth some effort, that's the bottom axis, and then they're going to gradually see more value. Now, which of these adoption functions would you prefer? We do not want our adoption function to look like a step function, especially not a high step function, where you got to put in a lot of effort before you start seeing value. Oh, I got to start annotating all my code. I got to start migrating to some new system, or rewrite fresh from scratch, or do some other painful thing before I see value. Some will use it, but it's going to hurt adoption. The ideal is to have a ramp where an adopter can start putting in a small amount of effort and already see value out of that. That's what makes adoption easy, and they'll want to do more. Well, to enable that, you have to have pretty high compatibility with NewThing. Otherwise, they'll never be able to do just a little bit and start seeing value. The minimum bar here pretty much always is that the NewThing can seamlessly use the NewThing. And ideally, you want it to be in the other direction as well. So there's a good story and a great story here. The good story is you at least want to build a staircase, which isn't a big step function. It's a series of little steps where an NewThing project can add NewThing side by side and start seeing benefit. For example, I have my new language, and I can put it in an old language project, maybe in a separate file, a .newlang file, but it can seamlessly call back and forth with old lang, or at least into old lang at a minimum, and I can use them in the same project. That already gets you into this nice and good place. But this is only good. The grail, the holy grail, is I can go to an old thing project. I can start using NewThing in just one small place and start seeing benefit. That's the adoption ramp. For example, I want to be able to write just one line of code in NewThing in this old thing project and start to see benefit. And some languages have done that. If you go back to the 1980s, since the 1980s, you could pretty much rename .c to .cpp, add one class, and it all works and you start seeing benefit. In the 2010s, TypeScript did the same thing. You can rename .js to .ts, start writing one class, and start seeing benefit. That's a compelling, easy to try adoption story, and it relies heavily on having designed for compatibility from the start. Ramps are for industrial use. So we talked about C++ before, but now let's talk about compatibility. It's not just that every C program is a C++ program and C++ code can seamlessly call C code, but we also leverage the optimizer, the linker. And so there's always been that parity. TypeScript, every JS program is a TS program and can seamlessly call the JS code. Now look at Swift and Roslyn again. Swift has bidirectional interop with Objective-C. Each can call the other. That is by design. It requires that they have similar object models and similar lifetime reference counting models. And that isn't an accident either, because if you've used Objective-C and you know about its automated reference counting and its modules features, well, those were designed for Swift before Swift was announced. So already they were building the on-ramp, that first part of the on-ramp, before Swift even had a name. The ramp was starting to be built. Roslyn was a precocious project. Sure, let's take a very popular million user plus language and change the compiler. Just rewrite the compiler. How many of those projects have you seen fail? Lots. This is a success story. And one of the reasons, talking to the team, is there were strict compatibility requirements from the beginning, including a rigorous adherence to a suite of compatibility tests. Otherwise, that would have failed. But it succeeded, and it wasn't an accident. The compatibility was by design. If you don't have it by design up front, often it's hard to back into it later as a retrofit. Unlike JavaScript's transition and complementary use with TypeScript, JavaScript and Dart is a very different story. And this isn't the only difference between Dart and TypeScript, but it is a major one that explains the difference in adoption of those two. Of course, a lot of people are familiar with the Python 2.x to 3 transition. For those who aren't, it was a source-breaking change. They decided to clean up the language, but also to break the language in a way where the same construct means different things in the two languages. For example, integer division gives you different answers in the two languages. And that explains why you can't just compile a version 2 file as a version 3 Python file. They'll do different things. And there are lots of migration tools. 2 to 3 gets you most of the way there. You have linters and checkers. But even almost a decade later from when this was first released in version 3 in 2008, most code was still written in the intersection of Python 2 and 3, which means it wasn't using most of Python 3's features. One of the problems with lack of adoption is people don't get the new value you're creating because they're still attached to the old value. And give or take, it looks like this one was about a 12-year transition, mostly done, still partly in progress, because in the latest developer surveys a few months ago, about 10% of Python users were still using 2.x, even though as of January 1st of this year, it was frozen and unsupported even for security fixes. It just goes to show how difficult a lack of compatibility makes. Now compare that to the first 3 versions of Python, which were spaced 8 years apart. It took 8 years to get from 1 to 2 and from 2 to 3. It's been 12 years since 3, and we've just mostly got people off 2. Another example from C was, as C evolved and made its second standard, C99, some of the additions were controversial and were actually resisted. Compilers were slow to implement them. In fact, tying it back into Python, cool fact, CPython actually only allows about 6 of the new features in C99 so far, primarily because compilers didn't implement them. And so they weren't available portably. So there's an example of one of many programs that just wouldn't adopt C99 or couldn't because it went in a direction that broke some forward compatibility. So what did the third C standard do in 2011? It actually created the idea of optional components that you did not require for conformance and immediately applied it to 2 previously required features, variable length arrays and complex, which suddenly were no longer required. And suddenly there were more conforming implementations of C compilers, because now all they had to do was essentially provide a macro that said, no, I don't support this. That's a one-line implementation anyone can do. C++ is largely highly backward compatible. It always has been, that we've touched on with C and with C++ previous. So 2 of the pillars we've talked about so far, the value prop and the bridge. The value prop for C++ is to be efficient and close to the machine. The bridge is that compatibility. It has always been about those 2 things, not about just one or the other. So when people say which one's more important, the answer is yes. They're both important. We wouldn't have C++ in as wide use today, for good or bad, if it weren't for that compatibility. But sometimes we have broken compatibility in small ways. So for example, the C++ 11 standard changed the requirements on the standard string type to ban certain previous implementations. It took 10 years until Red Hat Enterprise Linux, for example, and they're not the only one, shipped a conforming string by default. That was a long transition to get over what was an ABI breaking change, even though there was a lot of pressure to ship the new thing because string was a very common type. Nevertheless, it took a decade and more, and it's still reaching some platforms even right now as we speak. So this is what a decade looks like. Have you noticed that we've talked about a decade often? C lost a decade of full conformance in the industry until it walked back a couple of features where it went in a direction that customers weren't willing to go. C++, Python each lost a decade. If you don't build a strong backward compatibility bridge, you may still be successful, but it's probably going to take you a decade longer to reach that success than if you had designed for backward compatibility from the start. Let's just talk about 2 specific compatibility pitfalls. One of them is an annotation requirement. If you hear somebody come up with a new thing that says, oh, all you have to do is annotate 10% of your functions or more, especially if it's viral, that is a huge adoption step function. Now, especially when it's viral, there's 2 ways, downward and upward. The viral downward is to say, oh, a NewThing function can only call other NewThing functions. Say it's given an annotation like safe, or we usually talk about it like colorizing functions. Well, that means that before I can compile my new function in the middle of the call tree, I have to go down and update all the ones below it. That's a bottom-up annotation of the call tree. That's a lot of work, plus it canonizes a dialect of the language, typically. But the bottom-up, the upward coloring also can happen. Java checked exceptions is a great example. Before I can call this function, the caller needs to know about my color of function. And if there's an opt-out, like, I don't want to annotate all that, throws exception is basically a way in Java to just opt out of that and not color. Both of these are viral and they're adoption blockers. We see this happen in many, many safe C dialects. So creating a new safe C dialect is pretty much an annual indoor sport, probably many more than one a year. Here are just a couple of major ones, both no longer being supported. But you'll notice that in addition to binary compatibility with what pointers look like, annotations was a problem. The amount and the virality of annotations required on pointers in these particular dialects made them too hard to adopt and use. In fact, C Cured, after first shipping in 2002, 2005, produced a retrofitting paper that tried to help you to actually do the annotations as well as extend the pointer type system so that the incompatibilities hit you less often, but it still wasn't enough for it to take off. And one of the more recent entries in this space is Checked C from David Tarditi. And notice that it's distinguished by what we're talking about here. It's going to try to focus on backward compatibility and incremental conversion. So David here is answering what makes yours different from all the other safe Cs by saying, because we're going to focus on backward compatibility and making it easy to adopt. That is a strong answer. Don't know if it will succeed. This is one of those necessary but not sufficient things. But that's the answer you want if you don't want to lose a decade on your adoption curve. The last pitfall is a false friend incompatibility. False friend in natural languages is when you have the same, what looks like a similar word in two languages, but they mean totally different things. So you think you know it, but you don't really know what it means. That's what happens when you make 3/2 do different things in different dialects of Python, for example. If you have that where the same code can mean two different things, you're already in a sea of hard choices. You can either allow them both in the same source file, in which case you can't just look at that code in isolation and know what it does. You have to look around in the context to see what mode am I in, or which version or meaning of the code am I using, which makes it hard for code readers, for refactoring tools. Yes, people and tools can learn that, but it makes it harder. Poor choice number 2 is just don't allow them in the source file. Embrace that you're two different languages and go for a side-by-side play instead, where I use NewLang and OldLang, or V1 and V2 in different files side-by-side, which makes those problems not go away, but a bit more manageable. So what have we learned? How can you answer, why will your new thing succeed when these other things that tried to do pretty much the same thing failed? Comes to your value proposition. Attach it to an old thing pain. If it's a real pain point, you won't need to explain it very much. Make it available everywhere old thing is sold and used. It requires explicit design from the start. And make sure you have a compatibility bridge that's based on seamless interop with the old thing. That also is hard to back into later. And if you don't do number 3, you're going to slow down your adoption by about a decade. You may still succeed, but it will be slower and you're going to hurt your adoption. So finally, here's a specific case in point. People sometimes ask me, well, boy, C++ has problem XY that I don't like. What about a successor language? Well, every new release of C++ is a successor language. So far, the only language that has competed with C++ and replaced it in the market is C++ Next. But a new lang could do that too. So what would be necessary? Many have tried. What will make your new lang that tries to do this different from all the other ones that have tried and haven't done that yet? Well, focus on the value props, solving which C++ pain. Most of them get this one right because they can talk about things like type memory and concurrency safety, tooling complexity, complexity of the grammar and semantic special cases, those kinds of things. So that's not a differentiator. Availability, most of them have pretty decent availability. If you build on LLVM these days, you have pretty good reach to start, although you really want to integrate with native tool chains. But most of them do a decent job on number 2 as well. That's not a differentiator there. So why will your C++20 successor succeed when all these others haven't yet? Well, here's a differentiator that so far only C++ Next has tried because it's legit difficult to do. And you'll actually see this explicitly said on some of the language's websites. Designed for seamless interop with C++. That is not easy, but any language that does it will be able to do the same thing that C++23 and C++26 will do. That's hard to back into later. Now, if you don't, that doesn't mean you won't succeed. Languages are out there now that are growing, and they may well still succeed. But it's going to take them 10 years longer because they haven't done this. You want to have the grail of, I can write even one line of NewThing inside a C++ file and see benefit, or at least use them side by side. So as we look at that shining city on the hill, let's be clear about answering. Why will yours succeed when these other similar ones have failed, especially with a focus on compatibility and interop? Thank you very much for listening. And as we all endure this together, be safe, everyone. Bye now. And back to you, David and Christina.